An ellipse is a set of points in a plane such that the sum of the distances from two fixed given points, and these are called foci, which is just the plural of focus. There's now going to be two of them, remains constant. So the sum of these two distances remains constant and is equal to 2 times a. That's the definition. For the standard form of an ellipse, the value of a has to be bigger than the value of b, which means the a term, whichever one's got the biggest denominator, that's the one that gets listed first. It makes a difference. Okay? The bigger number is a in the bottom. You still have x minus h quantity squared. You still have y minus k quantity squared, just like a circle. The difference is the coefficients are not the same. That's the difference. So if we go back to general form of ax squared plus cy squared plus bx plus ey plus f equals 0. If a and c are equal, what kind of conic section is that? That's a circle. If one of them is equal to 0, what kind of conic section is it? That's a parabola, because that means one of them's not there. Okay? What makes something an ellipse is that A is not equal to C, but they have the same sign. They're either both positive or they're both negative. That's what makes something an ellipse. They are not equal numerically, but they have the same sign. They're either both positive or they're both negative. That's what makes something an ellipse, as opposed to a circle. Circles are very special kinds of ellipses. It's kind of like right or equilateral triangles being a special kind of triangle in general. It's the same kind of thing. Okay, circles are much more specific because the coefficients are the same. Now here's how everything works, and here's how all these relationships are. Whichever denominator is bigger, that comes first, but notice that the values that are used in the numerators, x minus h and y minus k and x minus h, those don't change from version to version. Whatever is underneath the x value, that's the direction that you use that number. So if a is underneath the x, then you use a across the x-axis right and left. If b is underneath the x value, then you use the value of b to go right and left. And you use the value of a to go up and down. That's what changes the orientation of an ellipse. Not which one's on the left-hand side and which one's on the right-hand side necessarily, but whichever variable it's under, that's the direction that you use. And it does go right back, just like with the parabolas, x-axis and y-axis. If it's underneath an x, it goes right and left. If it's underneath a y, it goes up and down. Okay. The vertex, or the center, sorry, is at HK. That's the center. There are two vertices on the major axis. There's two different kinds of axes. There's a major axis and there's a minor axis. They are exactly what they one and another. The names imply the major one's longer than the minor one is. That's the difference. Which one's longer? So on the major axis there are two vertices, and you find those vertices. This one would be a vertex in this picture, and this one would be a vertex. You start at the center, and you add or subtract A in whatever direction you're going. If you're going to the right and to the left, then you add and subtract A from the X value. If you're going up and down to get your vertices, then you subtract and add A from the Y values. Because if you're going up and down, the Y value is changing. If you're going right and left, the X value is changing. The foci, you can find those by starting at the center and adding or subtracting this value called C. Now this is the first time we've run into this C value. This is not the center, this is a length. Okay, this is a length. So moving on down here, so just to label the diagram here, the semi-major axis is from the center to either vertex. And for an ellipse, that's going to be the value of A to either vertex, and you can do it to either side. The semi-minor axis is from the center to the end point of, or to the end points of the minor axis. These are not called vertices, they are called the endpoints of the minor axis. They are not vertices. That is this distance. Those two values will come straight from standard form. The square root of one denominator and the square root of the other denominator. One's going to be A and one's going to be B. The distance from the center to a focus. The distance from the center to a focus, that's the definition, and that is what that C value is over here that we're talking about. The distance from the center to either focus is that distance of C. And there is a quadratic relationship that relates A and B and C. This is C, this distance that I've got highlighted in green. This distance from the center to the endpoint of a minor axis is B. And this has to be A because of the definition. The definition says that the sum of the distances from two fixed points remains constant and is equal to 2A. So if you use the endpoint of the minor axis and you draw segments to both foci and they have to add up to 2A, then because this is an isosceles triangle, because this piece is equal to, and this piece is equal, that makes it isosceles. That means these have to be equal, and they both have to equal A. That's a right triangle. The Pythagorean theorem says that A squared, you're not used to this because this time A is the hypotenuse, not C. A squared is equal to B squared minus C squared. You solve that for C. We'll do that right here. A squared is equal to B squared plus C squared. So C squared, solving that, is equal to A squared minus B squared. That is the quadratic relationship that remains, or that is found after you know what A squared and B squared is. A squared is going to be one of your denominators, B squared is going to be the other one. You always subtract the smaller one from the bigger one, and then C will be the square root of whatever that ends up being. Okay? That's where they come from. Now, just to kind of illustrate this, because it's great to take things on fact, but Mr. Tierman sent me this, and I'm just going to kind of illustrate it. This is the standard form of the ellipse that they have graphed here. I can't write on this, but the bigger number is 64, so that means that A is 8. The smaller number is 25, that means that this distance is 5. Notice how they have this listed at 5 and negative 5, at 8, negative 8, and positive 8. Look in this box right here. When it's drawn to the endpoint of the minor axis, this is 8, and that is 8, and it adds up to 16. Now watch what happens when I move this point. Just watch what happens. I'm moving the point around the ellipse, and it doesn't matter where I move it to, they add up to 16. Every single time. It does not matter where I move it to. I can move it all the way around here, still adds up to 16.
I can put it almost at the end point of the major axis. Still adds up to 16.
You can see the individual lengths. This length on the horizontal axis, that's 14.2, and the distance from the y-axis to that point is
1.8. And as you move it around, those values change, but they constantly add up to 16. That's where the definition comes from. Okay. Now there is a special relationship between the A value here and the C value here. That's called eccentricity. Eccentricity, and I'll come back to this in a second. Eccentricity is the ratio of C compared to A. And how that works is the closer that this ratio gets to being 0, the closer your ellipse is to being a circle. That's what eccentricity is. As the foci move closer to the center, it becomes more and more of a circle. Now, how does that look? This is actually a pretty neat thing here. Where was it? Was it this one? It was this one. Okay. Start with an ellipse, and as I move, watch what happens. This is your eccentricity ratio right here. Okay. A compared to C. And as I move that closer to the center, look what is happening to the ratio. It's getting smaller and smaller and smaller. And the closer it gets to being 0, the closer you are to being exactly, and I don't know if I can get it exactly at a circle. I had it there. Oh, I had it and I lost it, sorry. But you can see as you move this away, the bigger the ratio gets, the more elongated it gets, and the smaller the ratio gets, closer it gets to 0, the more it becomes a circle, because the foci end up actually being on the circle when they're equal. Okay. So that's just a little bit about eccentricity and how the definition works. Here's how you actually use it. Now these first two are in standard form, so we're going to pull the information out, and I'm going to show you how to use it to graph. And then on the back, I think there's 2 more that are not in standard form, and we'll do those all the way through. So here we go. This is in standard form. X squared plus, or x plus 2 quantity squared over 25 and y squared over 9. Find the center, the foci and vertices, and then graph the ellipse. Now here's how I recommend that you do this. You always everything starts at the vertex, or the center, sorry. Center or vertex, depending on which one you have. It starts at HK. In this case, it's the center. Where is the center of this ellipse? -2, 0. All right? And then you do the ABCs. The value of A is the square root of the bigger denominator, so that's 5. The value of B is the square root of the smaller denominator, so that's 3. And then you calculate the value of C. C squared is equal to A squared minus B squared. So in this case, C squared is equal to 16, and that makes C equal to 4. 25 minus 9. Pretty sure that's 16. Square root of 16 is 4. So now we have the ABCs. You start at the center and you use them in the same order you found them. You start in the center, you use the A, then you use the B, then you use the C, and you label your points as you go along. All right, so here's how that looks. -2, 0, put the point there. A is 5. Now the big decision you have to make is which direction do you use A and B and C. The A value came from underneath the X, so you go from the center 5 units to the right because you're adding 5, and 5 units to the left because you're subtracting 5. That's what that formula was that I gave you up on the side right next to the ellipse, where it said center plus or minus A to get to the vertices. That's what that meant. You start at the center, and if this is 5 units, you go 1, 2, 3, 4, 5. That's a vertex. And that vertex is at 3, 0. Then you go 5 the other direction. And that's a vertex also. And that's going to be at -7, 0. So there's your vertices. And we used our A value. B is always in the opposite direction of A. So if you went right and left with A, then you go up and down with B, in this case 3 units. From the center again, 1, 2, 3. 1, 2, 3. Do not label those as vertices because they are not. They're just point. You don't even have to give me the coordinates of those things. You just have to have them to graph the ellipse. Then you use C. A and C always go in the same direction. Always. Because the vertices and the foci are always right next to each other. Okay, so if the C is 4, then we go 4 units to the right, which is there, and 4 units to the left, which is there. And the coordinates of that are going to be 2, 0, and -6, 0. And I did everything and found the center. I found the vertices before I found the foci, and that's the way I recommend you do it. You just do it in alphabetical order. Don't jump around because it's easy to get them confused. And then the vertices connect to the minor axis endpoint, connect to the vertices, connect to the minor axis endpoint, and goes all the way around. Now, please understand that ellipses do not come to points at the vertices. These are not football shaped. They're more, if you are looking for something, they're more rugby ball shaped. As a matter of fact, I think a rugby ball is an ellipse, a real one. They're very rounded on the end. They do not come to points. Okay? They do not come to points, and that's how you graph an ellipse. Once you pull those pieces of information, you will graph everything exactly the same way. Now, how they're labeled may be different, and that's why I put number 2 in here. Number 2 is almost ready to go, but this is not in standard form. Why? The denominator on the y is bigger than the denominator on the x term. You're exactly right, and like 3 of you said it at the same time. That's great. So standard form, you need to switch these terms. Y minus 3 squared over 8 plus x minus 2 squared over 6 equals 1. They did ask you for standard form. You will need to list that. So that's not going to change what you know about it, but you do need to put it in standard form. So you start at the center.
Will they always equal 1?
They will always equal 1, and I'll show you why when we actually start one with general form. Okay, but yes, they will always equal 1. They will always equal 1. So where is the center? 2, 3. And what's the value of A? Two radical 2. And what's the value of B? Radical 6. And then C squared is equal to A squared, which is 8, minus B squared, which is 6. So C is equal to, if I do this right, square root of 2. Now, when you label things, these are the values you're going to label. When you plot them, you're going to need decimals for all this. But you don't ever label using the decimals. You use exact values to label. You use the approximations to graph, to plot. All right, so 2 radical 2, I'm thinking that's like 2.8-ish. Radical 6, I don't know what that one is. 2.4 maybe, 2.3, 2.4, thank you. Radical 2, I know that one is 1.4. Now we found everything we need. Here's how you use it. You start at the center again, so start at the center. 2, 1, 2, 3. Now you use A and then B and then C, just like we've been doing it. Which direction do you use A? Up and down, because 8 is underneath the Y term. So 2.8, and you're going to have to approximate that endpoint on this graph. 1, 2, we'll call that 2.8 up there, that's going to be a vertex. Down 2.8, that's going to be a vertex. Okay, now, how do you label these? You start at the center. Okay. When you move up and down, which coordinate is changing? Is the x value going to change, or is the y value going to change if you went up and down? The y value only. So that means that the x value does not change. Now, we started at 3, right? Because that's the center. We started at 3, and we went up 2 radical 2, and we went down 2 radical 2. So you write that by saying plus and minus 2 radical 2. And those are your 2 vertices. Does that make sense? Do y'all catch that? Okay. If we were going right and left, then it's the x value we would have adjusted. The only time this notation is acceptable is if there's a radical involved. If this was a 3 plus or minus 3 and you left it like that, I would count it wrong. Because you can add 3 plus 3 and you can subtract 3 from 3. Okay. If they're exact points, you need to list them as exact points. If your points are approximated, then you may use this plus or minus notation. Only if there's a radical involved. Okay? If there's no radicals involved, then you don't use this notation. You do it more like what we did over there. You list the points individually. 3, 0, negative 7, 0, or whatever the case might have been. Now we're going to use B, which is 2.4, and because we went up and down for the vertices, we're going to go right and left with the foci. 2.4, 2.4. We don't need to label what those are because they're just endpoints. They are not foci or vertices. And then the foci are always in the same direction as the vertices, but these are 1.4, so go 1.4, that's a focus, and just label it with an F. And then come down here, and we're going to do the same kind of thing here. We started at 2, 3. We went up and down. We went up radical 2, and we went down radical 2, so you write that as plus and minus radical 2. And then remember that the ellipse goes through the vertices and the endpoints of the minor axis. You really don't have to have the foci on the graph in order to draw the ellipse, but I'm recommending that you put them there, do things in alphabetical order, use the A, use the B, use the C, get the points on there, because if you draw the ellipse in first, you're going to probably forget to put the foci in on the graph. Okay, so just start with the vertex and then alphabetical order and end up with the graph of the ellipse. Okay. All right, so the next two are not in standard form. That's going to be your first step. Identify the center, the foci, and the vertices. All right, now here's where it's different. You take a look at the x squared term and take a look at the y squared term. There's a 4 in front of this one and there's a 1 in front of that one. That's what makes this an ellipse, not a circle. If it would have been a 4 and a 4, you divide everything by 4 and that's a circle, if they're the same. They are not the same. So when you do this, and I'm going to do this the first time in separate steps so you can illustrate, you still attack it the same way. The x's go together. The y's go together. anything that is a constant term goes on the other side. You start these exactly the same way as you started circles. Now you cannot complete the square with that 4 there, so you have to factor it out. And that 8x tells you you're going to have to complete the square, so we're going to go ahead and start to complete the square. The coefficient of y squared is 1, so there's nothing that has to be factored here. But you can put a 1 there in front of it just so that you know that you did it. And that 4y tells you you're going to have to complete the square for y. And then remember to balance the equation. Now, has anybody in here not taken chemistry? Okay, then you'll kind of understand. Remember when you're balancing equations and you're dealing with molecules and atoms at the same time? It's one thing to balance it by just putting a blank there, but you got to remember that there's a 4 out in front of this one. So on that side, you need to make sure you put a 4 in front of one of your blanks, because if you don't, it's no longer balanced. It's not just about the number of atoms. You have to count for the number of molecules that you started with also, if you want to draw parallels to chemistry class. Now, at this point, you do this exactly the same way as you would have done a circle. Once you get it set up to complete the square, you fill in the blanks, you factor it the way it's supposed to be factored, and then you get it to where it needs to be. So that's where we're headed. Half of -8 is -4. And half of 4 is 2. And then do what it says. This has still got a 4 on front. Don't just get rid of it. It's still there. X minus 4 squared plus, you can put the 1 there because this is not going to be your last step. Sorry, the y squared does not go on the inside. The square goes on the outside. All right, did anybody add up the other side for me? I think it's 4. All right. Now, had this been a circle,
These two numbers would have been the same, and you would have had to divide it out at the beginning. This is an ellipse, and you know that because they have different coefficients, and ellipses have to equal 1. So whatever this number ends up being, you divide everything by that, and then that will put it in standard form. Ellipses have to equal 1.
so everything is divided by 4, and I would not recopy anything just yet. That's going to give us the 1 that we needed. And I say don't copy it yet because you got to remember to cancel. That makes that a 1. And when you recopy it, you want to put the biggest denominator first because you want it to be standard form when you're done. So you're going to end up with y plus 2 squared over 4 plus x minus 4 squared. And you may leave it just like that. However, I don't like doing that. It is not wrong and will not ever be marked wrong. I like to put it over a fraction so that I can visually see that I've got where my denominators are. You don't have to do that. If you want to just know, that's okay too. All right, so we got standard form. Where is the vertex? I'm sorry, where is the center? Nope. 4 and -2. X always from the H term, Y always from the K term, or K always from the Y term. So there's your center. It's the value of A. 2 and B, 1. And then C squared is equal to A squared, which is 4, minus B squared, which is 1. So C is equal to the square root of 3. Get a decimal approximation for that. It's like 1.7 if I remember from geometry. Okay. Now we're ready to do the graph. Start at the center. 4, 1, 2, 3, 4. down 2. There's the center. Check. Are the vertices right and left of the center or above and below the center? Above and below, because the bigger denominator was underneath the y. 2 units up, vertex, 2 units down, vertex. These are exact pairs. There was no radical involved in plotting those 2 points, so plot them exactly. This one's going to be 4, 0, and this one is going to be 4, negative 4. Then you use B, which is 1, and that's both sides, always perpendicular or always the opposite direction of A, always. And then you use C, always in the same direction of A. So up 1.7 and down 1.7. You can draw the ellipse in now if you wish. Bless you. All right, now the foci. We started at the center, which was, and which one's going to change, the x or the y? The y. So the x does not change, but the y does. We started at negative 2. And we went up radical 3. And we went down radical 3. From here on out, I don't expect you to show me this first step up here. That was just to illustrate what you're doing. You can go straight to this. If it helps you to show me, to write that down so that you can see things together, that's fine. But that is not something that you have to have. That was an illustration step. So when we go on and do this last one here, we're going to factor a 4 out of the x's, and we're going to factor a 9 out of the y's. And now at this point, I'm going to go and I'm going to look. There is a linear x term, so I'm going to have to complete the square, and there is a linear y term, so I'm going to have to complete the square. The 4 goes on the outside. Don't forget you factored it out, so it's going to be minus 2x plus something. And then factor the 9 out of the y's, and it's going to be y squared. Minus 4y. And then on the other side, the negative 4. And now we got to balance the equation. We've got the blanks there, but what you have to remember is there's a 4 in front of that blank, and there's a 9 in front of that one. Once you get to this step, and I hope you're seeing the relationship between all 3 that we've done so far. The first step is always the same. You put the x's where the x's go, you put the y's where the y's go, you set up to complete the square. It doesn't matter what general form you're given, that's how they all start. Every single one of them. And once you get to this point, it's just about filling in the blanks, literally. Don't forget to bring the coefficients after you do the factoring. All right. I got 36. Is this standard form? No. How do I get it there? Divide everything by 36. Now you're going to want to do the canceling first. 4 goes into 36 9 times, and 9 goes into 36 4 times. So we are in standard order right now, so you don't have to change the order. Where's the vertex? I keep calling it vertex. Where's the center? 1, 2. What's A? And B? And C squared is equal to A squared, which is 9, minus B squared, which is 4. So C is the square root of 5. Help me out there. 2.2, 2.1, 2.2, thank you. All right, we've got everything we need. There's the center. That's where you start. 1, 2. Now we're going to use the 3. Which direction do you use the 3? Left and right. 1, 2, 3, vertex. 1, 2, 3, vertex. It doesn't matter what order you put these in when you label them. So this one's -2, +2. And this one is 4, +2. B is always in the opposite direction, so up 2 and down 2. Remember, you do not label those because they are not vertices. They are simply the endpoints of the minor axis. And then we use the foci, the C values, 2.2, focus, 2.2, there's 1, there's 2.2, focus. And then we have to label the foci. Now we started at the center. We went right and left. So which one of the center coordinates are going to be adjusted, the x or the y? The x this time. So we start at 1 on the x, and we added square root of 5, and we subtracted square root of 5. But we did not change the y value. And that, or those, are ellipses from beginning to end. Okay. Once again,